Hi, welcome back. It's been a little while since I've made some videos, so this might be a little rough, but I think we have some good examples here, and we'll just plow on and see how this goes. So the topic is implicit differentiation, and you might want to pause the video and record these four implicit functions. Their graphs are all different, and we will proceed to finding a line tangent to the first curve in this video, and it may be that we have to make subsequent videos to fit them on. Okay. For the purposes of implicit differentiation, we need to recall that we're going to assume y is actually a function of x. Think about the implicit function x times y equals 1. Well, we can rearrange that function so that y is by itself. Y is equal to 1 over x. And when we can get y by itself, then we can think of y as a function of x. X is the dependent variable, x is the independent variable, y is the dependent variable. There are other times, for example, if we're writing the circle centered at the origin with radius, well, let's make it radius 1. If we try to rearrange the terms and get y by itself, we will end up having to take the square root, an even root of both sides. And when we take the square root of both sides of an equation, we have to take the plus and the minus case. There would be two roots to that equation. So here y is not a function of x, because for each function of x there's two output y. But we could still restrict the range of this function. We can maybe assume that y is non-negative, and then that makes y a function of x, and we can proceed. So we're going to look at equations written in implicit form, and we're going to start by assuming y is a function of x. Now, why do we do that? If we're looking for slopes of tangent lines, we're going to have to take the derivative of the function. When we take the derivative of a function that's just written in terms of x, and we're taking with the derivative with respect to x, we use our basic differentiation rules. For example, the derivative of x squared is just 2 times x. On the other hand, we need to remember, when we're going to take the derivative with respect to x, and we have some function written in y, and we have assumed at the outset that y is a function of x. When we take the derivative, yes, we use the power rule, but we also have to use the chain rule. So the derivative of y squared is not just 2 times y, but the derivative of y squared is 2 times y prime. Okay. Let's look again at this list of examples here. We're going to first practice our implicit differentiation, and then we're going to use the resulting derivative to tell us something about the graph of the function. Okay. So let's look at number 1. This example comes from a textbook I've used, published. The author was named Larson. So we have an equation that represents a function. Well, it's a relation among x and y. And if we want to find y prime, step 1 is to take the derivative of both sides. We're going to take the derivative with respect to x of both sides. Takes a while to rewrite that, doesn't it? Okay. So the derivative of the left-hand side. Alright, since the only variable on the left-hand side is a y, and y is a function of x, we have to use the chain rule. The derivative of something squared, we'll use the power rule first, bring down the 2, keep the base, subtract 1 from the exponent, understood 1. But we need to multiply by the derivative of the base. The derivative of y is written y prime, and we know the derivative of negative 2 would just be 0. So the derivative of the left-hand side is 2 times the difference y minus 2 times y prime. The derivative of the right-hand side is much more straightforward. If you think about it, the right-hand side is just 4x minus 12. And the derivative of a linear function is its slope. Can you pause a moment and convince yourself that the derivative of the right-hand side is 4? Okay. So we have taken the derivative of both sides of the original equation. The next step is to get y by itself. Okay, so, we need to get y prime by itself. So any expression that doesn't have a y prime as a factor, we need to move that to the other side. Well, we can just divide both sides. Divide both sides by 2 times y minus 2. And we have an expression for y prime. Okay, now we use y prime to find the slopes of the tangent lines to the curve, the original curve. Let's pick a point on that curve. So let's consider the ordered pair 4, 0. You want to pause a moment and make sure that 4, 0 satisfies the original. Yes, if we substitute x equals 0 on the right, and we substitute, I said that wrong again. If we substitute 4 for x on the right, we'll have 4 times 1. If we substitute 0 for y on the left, we have negative 2 squared. And we can show that the left-hand side and the right-hand side are both 4. So this ordered pair is on the curve. Okay. Well, y prime can be calculated if we know x and y. If we look above, y prime is 4 divided by this product. So we need to take 4 and divide by 2 times the product of 0 minus 2. Only y showed up in the expression for y prime. So I had to substitute 0 for y. I simplify. And I find out that the curve is actually decreasing in the neighborhood of 4, 0. If you're asked to go one step further and approximate the curve using its tangent line, you probably will need to be able to write down the equation of the line tangent to the original curve, back up here in purple, tangent at this point, 4, 0, with this slope. Okay. Well, the equation of a line can be written as y equals m times the quantity x minus x sub 1 plus y sub 1. And in this example, we know the slope, which is negative 1, and we were given the specific ordered pair 4, 0. So we substitute in the slope, negative 1, and we substitute in the values for x1 and y1. So one approximation to the curve would be the line negative x plus 4. Okay, we'll stop here and finish the remaining examples. The remaining 3 examples we'll have in some other videos. Okay. Again, if these examples can be found in a Larson book. It's called Larson. The author is Larson. It's Calculus Early Transcendentals. And so this would be the chapter on implicit differentiation. I think that would be chapter 3.5. And they have some nice graphs. You can find this online, and I'll make that link to the publisher's website so that you can see the graphs to these.